Hi, I'm Nas. I'm the CEO and founder of Rebel and the author of Developer Life and maintainer of the Rebel TUI crate. I believe that open source comes from an open heart and from the joy of coding. So in today's live coding video, I am going to deep dive into the Rebel TUI code base to kind of highlight one of the issues I encountered recently while I was making some changes to the spinner component. So essentially, the Rebel TUI crates, actually let me show you a demo. What it is that it allows, it's written in Rust, and it allows you to create what I call full TUI applications, partial TUI applications, and very sophisticated CLI applications. So it's kind of like a spectrum of how interactive you want your applications to run in the terminal, and they can all run over SSH. So like a full TUI application is like a markdown editor, and something that's partial or hybrid, it's something that for some parts of the application it ends up taking the full screen, and other parts it doesn't. So one of the main sort of elements to display intermediate progress or indeterminate progress is a spinner. And so the spinner is used in the TUI, the full TUI, partial TUI, all of these. And to kind of complicate things further, everything in the Rebel TUI crates are async, and that actually required me to implement something that's the equivalent of readline but async. So the whole thing is sort of built on top of this completely async architecture, but that's not so important for this video. So let me kind of show you what the spinner is supposed to look like, and I'll show you what was happening. So kind of like the sort of the whole reason for me to do this is that a lot of times when a spinner runs, it essentially behaves as it's animated. It essentially prints some text, and then moves the cursor to let's say the beginning of a line, writes one line of text, waits for a little bit, writes a different line of text, moves the cursor, waits for a little bit, writes another line of text. And when you put this together over time, it delivers the illusion of animation. So essentially that's kind of like our eyes and our brains working together to make these lines of text look like they're moving. And so it's really cool, and it's a very effective way of showing, like, okay, something is taking some amount of time. And the kind of two behaviors are, while it's showing indeterminate progress, you can hit Ctrl+C and interrupt the spinner and the task that it's spinning on. If you hit Ctrl+C again, then you might actually exit the application itself. That's kind of like the behavior in the you get out of the box if you build an application using the Rebel TUI crate. So so in practice, this is what it looks like. So if you actually check out the Rebel Open Core repo, which I have on my computer, and go to the TUI folder, there's like one consolidated example now, and you will need to install new shell if you don't have it, but you can do that pretty easily. So with new shell, you can say run new examples, and that shows you. So this is an example of a full TUI app. So if here's a full-blown markdown editor with syntax highlighting for even code blocks inside of it, and I'm still working on this. But yeah, it's it has dialog boxes, auto completion, all kinds of stuff. So then the partial TUI is this thing, readline async. So this is kind of like, you can think of it as like if you wanted to make your own shell. So let's say, and you wanted that shell to, notice the prompt was still there while it was dumping output. So here's that spinner thing. So you hit spinner. So essentially, while the spinner is spinning, it pauses all the output to the terminal, which is really cool. Like, these are not things that you get out of the box with the readline syscall, which is blocking. And once you block it, there's no way to kill the thread that's blocking on that. It's a blocking call. So it leads to all kinds of problems. Like, you'd have to hit process exit or something awful to do that. Okay, so let's just focus on the spinner. So this is the spinner component. This is actually working as intended. What you're seeing right now, it's painting like these beautiful gradient colors, and it's kind of spinning over time. I don't know, depending on the quality of this recording, it may or may not seem that nice. But if you have 60 FPS, I don't think with my OBS I'm able to get that level of yeah, quality. But if you run this on your own computer, you'll see a really beautiful animation. So that is actually the animation working, and it wasn't. I made a fix to this last week, and this is what the video is about. Like, so what was happening was perplexing. And in order to get into that, I actually wanted to talk about println. So with the Rebel TUI stuff, I just touch upon like primitives that have been around forever, and I don't know, people don't even think about it much. Like readline is a blocking call, and if you have a process with thread and that thread is called readline, then that thread will be blocked until the user hits Ctrl+C, Ctrl+D, types something and presses enter. So, but Ctrl+C handling doesn't work like you think. It sends a signal to the process. So, and then the process might have to exit. But essentially, like once that readline thing is blocked and you haven't typed anything, and it'll just wait indefinitely. So, which makes essentially the interaction in that terminal with the user at that moment, it's frozen, which makes, if you think about that behavior, you can kind of backtrack into why command line applications expect you to type literally everything up front, because unless you do that exactly right, it doesn't really have a chance. So with the Rebel stuff, one of our remember I was talking about full TUI, partial TUI. The eddy is this you could say cargo install Rebel commander, but there's another thing called Gitty. Gitty is like a Git interactive, and essentially if you don't give it all the commands, it'll ask you. It's really smart. So it basically like so it's and I'll show you. I actually have an older version of Gitty installed on purpose so I could show Ctrl+C handling later. But yeah, essentially you can say, you know, Gitty branch and then new, and then it'll prompt you for a branch name. If you hit Ctrl+C, it's not a problem. Nothing is blocking. It's totally async. But the amount of work that went into making that little blinking line editor is immense. That's a readline async. So coming back to the spinner. So with the spinner, as it's spinning, it's printing stuff. So printing stuff, printing a line, which is a syscall, like a standard out, standard in. These are file descriptors provided by the Linux kernel. What you may or may not know is that every time you call println or eprintln, the system actually locks standard out or standard error before it prints. And that is the crux of what I was running into. So I had repeatedly, I had a Tokyo task, which was on an interval printing stuff. Like every time it printed, it changed the color, printed it again, waited, changed the color, printed again, waited, changed the color, printed again, waited. But every time it was doing this, it was locking standard out, because that's how this works. It was ultimately taking a bunch of a string, taking a bunch of color information, turning it into an ANSI escape sequence encoded stream, which is a bunch of bytes, and it sent that to the standard out, which is you can write to it. And but before the write could happen, a lock was being acquired. So you might have actually noticed this in other applications. If you write an application and you have multiple threads dumping to standard out, and let's say you have 3 threads, and you expect like thread 1 said A, thread 2 said B, thread 3 said C. Sometimes you'll see ABC, sometimes you'll see ACB, sometimes you'll see BCA. Who knows? Like that order is non-deterministic, and the reason it's non-deterministic is because of lock contention. So when those println statements, which console log, let's say, dumps you into println, it ends up acquiring a lock. And if multiple threads are in contention of acquiring that lock, or in this case, it could be multiple processes, because actually not multiple processes, standard out is for that one process. I'm sorry. So multiple threads within the same process are in contention for that particular lock, then who knows? We don't know. It's not undefined behavior, basically. Like we don't know in what sequence, if all 3 show up to acquire it, you know, who's gonna end up the lock. Typically, this is totally like a non-issue, but if you have multiple tasks writing the standard out at the same time, and you have seen this behavior before, like through console logs, like this explains why. And I ran into literally this. I thought I was doing so many things as debugging, and it turned out to be log contention. and the non-deterministic nature of this, acquiring this lock. So I had to come up with some crafty solution, which ended up making the code much simpler, and I will get into that right now. So that's what this video is about. So it's all about dealing with how do you think about acquiring a lock for something as simple as a standard primitive, knowing that if you have something like a spinner animation, how will that impact what you see on the screen? So I actually have an older version. This is all fixed up and nice, but let's work on an older version of this repo. Basically, this is the commit when this is the going back in time. This is when I actually encountered the problem. I actually was like, oh, I knew I wanted to make this video because this was puzzling me. So I ended up essentially making a commit to kind of freeze that moment in time. So let's go back in time with Git workspaces, and then we can actually see what the problem is, and the fix, surprisingly, isn't as complicated as the explanation. So let's do that. All right, so let's use Git workspaces to roll back time and go back to an older version. If you haven't used Git workspaces, it's really cool. It allows you to check out multiple copies of your repo in different top-level folders. So you can take a commit, you can say put this in folder A, take another commit, say put that in folder B, and then Git will basically keep track of all of them. It's really nice. I use it all the time for when I'm doing large rewrites and refactors. It's nice to know where certain files are at different stages in their life, and it just makes it easier. There's some, I'm sure there's ways to do this without using workspaces, but it's kind of nice. Plus you can open multiple vscodes or Rust rovers and just point them at different folders, and then that's just kind of you have different IDEs hooked into, or whatever, if you use Helix, whatever it is. It's kind of editor agnostic, or tool agnostic, I guess, because it's provided by Git itself. So the way this works is you have to be in the folder with the repo in it. Let's see, yep, I am in the folder. Oh, actually, no, I'm not. So this is so this has the Git folder, so you can see okay, I am actually on a newer commit here in this particular folder. And what I want to do is I want to tell Git workspace to create. Actually, let's do this. Let's see if I have a Git worktree. Oh, it's not workspace, it's worktree. Great, I got the command wrong right off the bat. Worktree. Okay, cool. So, oops. Git work. Why is it still wrong? Ah, because I was consistent in my. Let's see. Actually, worktree would be a better name. I don't know. All right. Okay, so Git worktree. This is, by the way, why I'm making Git interactive. It's because I don't want to remember all these commands that Git has and all the configuration. I just want Git to take care of it. I just want to tell, maybe I'll make a Git workspace command. Actually, that's a great idea. I'm gonna make that a feature. Okay, so now I have to make sure that, okay, this particular work tree doesn't exist already. So you can say git worktree list and get a list of your existing work trees. So now I'm going to say, okay, git worktree add. So I'm going to go up one to rebel open. Oh, this is typing it. Is this the correct SHA? I don't know. So spinner. This is actually the folder I want to put it in. This actually might be the right SHA. Oh yeah, it is. So okay, cool. So this ended up creating a rebel open core spinner folder. So I can do rebel open core spinner, and you can see that the SHA is, you know, whatever this is. So now I'm able to open vscode in this case. I use Rust rover and vscode for this live coding video. I'm going to use Code Insiders. It's just I use basically vscode and Rust rover for my production stuff, and Code Insiders for doing videos, because that way they don't get all mixed up. Let me actually close these because we don't need this anymore. I don't think we need this terminal anymore. Move it here. Okay, so let's see. Okay, so here we have, actually, you know what? I'm going to take this off the screen completely. There we go. Okay, So let's see, git worktree. Actually, you know what? I'm gonna move this back. I like to see the nice transparency, so you can see the nice 8-bit backgrounds through this VS Code. Hopefully, it makes for a more pleasant viewing experience. Okay, so let's open a terminal. Actually, I had a terminal. Ugh, okay, I guess I'll bring it back. All right, so so we have, let's say, okay, so we want to go to the TUI folder, and then we want to say new run new examples, and notice these will not work. This should actually, let me see, this is oh, actually this is not gonna I need to patch this commit with this is a bit of a complication, but let's do this. Spinner. This actually is the I realized once I made the commit that I had this example was not demonstrating the problem, so I had to patch this example, and I have that here. So I'm just going to load up, and you can get it here. I have it linked to this one, the TUI example spinner. That's not in the commit. You can download it from there if you're going to follow along. So let's go to spinner, and let's do this. Let's do cat. I'm just gonna grab this and put it here. Okay, so let me change this. So okay, by the way, this command set clip get clip, these are just fish scripts that I've written to make my life easy, and I'm planning to rewrite all my fish scripts into Rust. I already have a Rust script. It's built into the Rebel TUI crate, which makes it very easy to use Rust to write scripts, and you can test them. And you have like enums and type safety and all kinds of wonderful stuff. It's much more maintainable. There's modules. Yeah. Okay. So so now actually we can run this example and see it fail. See. So pretty unfortunate. This is somewhat of an elaborate setup just to kind of show this problem, but there it is. Okay. So it's painting a line. Then it says, notice that something is wrong. Even without knowing what this is supposed to do, that doesn't look great. As you can see, like stuff is getting clobbered. And I spent hours and hours and hours, almost like a day, rewriting how standard out, like how the text or bytes are being printed to standard out. I tried this, that. I thought it was like some terminal problem. Tried different terminal emulators. I was like, oh, is crossterm doing something strange? Wrote the ANSI escape codes with or without, and changed all the everything, and it, no matter what I did, it would do this. And the weird thing, and the weird thing is that it wasn't even consistent. So it would like flake out. Sometimes it would work okay. Sometimes it would. Like right now, it's pretty consistently flaking out, which is pretty awesome. But that's the beauty of this lock contention, is we don't know what's going to happen. That's the whole thing, is that you could run it a few times and it works fine. Other times you run it and it's not fine. Okay, so so there you go. It's pretty consistently not working. So what's supposed to happen is that if you look at the code, it's supposed to print one line saying like what's about to happen. Then it's supposed to spin the spinner, and when the spinner is spinning, the message is, this is an indeterminate progress message trying to connect. Once it finishes, it's supposed to say, this is a sample final message connected. And notice something is wrong. Something has gone awry with this example, because you can see like shadows and stuff. What's supposed to happen is supposed to say, okay, example without concurrent output, Braille, and then it's supposed to say, I'm trying to connect to a server, color change, color change, color change. Oh, I've connected to the server. And all in the same line. So this is without jumping up and down. And so this is giving the illusion of an animation, like what this is. Oops. this is the fixed example. Notice there's the, it says whatever. I'm trying to connect. Okay, spinning. I've connected, and that's pretty much it. We're going to totally ignore this concurrent output part because that's not the problem. So if we look at this example, so we're actually going to focus in on this without readline async, because we don't care about that for the purposes of this video. We're also going to ignore this line. I have a whole video coming up on memory latency and locality, which I've been working on for months. So that's I will do that soon. Let's see, without readline async. So this is the one we're focused in on. This is like, okay, what is happening here? This is just like you're making a simple program. You want to start a spinner, have it do spinny things. While the spinny thing is happening, you have another Tokyo task actually doing stuff. When that Tokyo task finishes, it should just nicely signal the spinner and say, hey, stop. And then the spinner should stop, print the final message, and you're on your way, right? Pretty straightforward. It's like the life cycle is somewhat simplistic. You in a Tokyo context, you start a spinner. It starts spinning immediately, dumping stuff to standard out or standard error, whatever you choose. Then when that task is finished, the other task, then it should signal to the spinner that it should stop, and then it can resume. So pretty straightforward life cycle. I mean, at a high level. We're not getting into too many details of how it's done yet. So let's just look inside. And the spinner, if you can ignore some of this noise, there's actually 3 different styles of spinner. I've actually dropped one of the styles, so this one has 1 extra style. But Braille is kind of like my favorite. This is what it looks like. This is the fixed. So this is Braille. I don't know if you can see that on the bottom of the screen. And then the other one I think is called something, block or something. Okay, so this is actually the code that's running. So it goes, all right, this is my message. I'm trying to connect to a made up message. This is the indeterminate message. And then it goes, shared write, ignore this. This is for integration with async readline, which we don't care about today. So it just gets a mock shared writer just to make the API happy. And then it goes, okay, here's the code. So start spinner. It goes, spinner, try to start, given this message, some configuration about the style and how often to spin. And this is like, okay, should I dump the output to standard error or standard out? And it's irrelevant. This bug happens whether you put standard out here or whether you put standard error. Irrelevant. They both exhibit the same problem because standard error also is afflicted by the same exact non-deterministic lock acquisition. Okay. So, and then it goes, okay, just wait for some time, just simulating some background task or subtask is running. And then it goes, all right, when that task is finished, go ahead and stop the spinner and go about your day, basically. So this is you say try start, do something, and then when that thing finishes, it goes, all right, stop. So if we look at the try start, this is a bit more sophisticated. What is happening now? So what it does, it's an actor, and what it'll do is it'll set up a essentially a shutdown channel, and it'll create a spinner struct inside of which will store a bunch of information, and then because it's an actor, it'll spawn a task, a long running task, which will continue running even when this function exits. And that long running task happens, this function, this associated, that's a method. Oh, okay, this method basically kicks it off. And so what this does is that this is doing all the work. So before it, spawns something in a loop, it does a bunch of setup, and then it creates an interval. Not a this is the right way to do recurring tasks in Tokyo. And then it goes, all right, in a loop, I'm just gonna pull the interval to see, okay, do I need to the reason there's a render and a print is just overly complicated. Essentially it's because there's different styles. So the render phase, it'll take the style and generate the bytes, and then the print will actually take those bytes and print it. So notice here it's locking whatever was handed to it, this is basically a safe output terminal. This is basically just a type alias. It just says it's just saying that, okay, whatever it is, this thing is, it can write and send. And we're actually using if you look at try start, when we called it, we passed it basically a standard error in this case, and so it's just a wrapper on top of standard error. This might and there's a reason for wrapping it so many times. We'll see it in a minute. So roughly, you can kind of, if you squint your eyes, essentially this is just where is it? This is just standard out basically. This whole gobbledygook. It goes something like, all right, print tick, and what print tick does is that this actually drops down into crossterm and uses ANSI escape codes to generate the desired output. So here, what tick does is that it just, think of it this way, moves the cursor to the start of the line, prints something, and that's essentially it. There's a lot more detail into what's happening here and how to make it happy for this and the readline async use case, but again, no matter what we did here, this problem was not going to go away. The problem lies elsewhere. So then after it just kind of keeps taking the prints as long as there's a valid interval, it's not been dropped. And eventually when this task, this, let's say, quote-unquote long-running task finishes, it just goes, hey, spinner, go ahead and stop. So then that's the stop function or method. And this is where the problem is. So essentially between the this line, so this is every interval that happens. I think it's expires. No, not expires. Whatever. Every tick that happens, reached. Every interval that's reached. It locks essentially acquires this lock, which is just to get access to standard error in this case, and then it prints something. So even if we remove this safe output terminal, it would still be you would still see the same problem, because ultimately to acquire standard out, no matter what, there's a lock that has to happen. There's a reason to wrap this, but it has something to do with readline async, which we don't care about for this example. So okay, so this one, there's some lock contention here before we print the tick. And when stop gets called, so basically think of it this way: once the try start, the mental model of your program is like, okay, try start initiates tick, it's ticking, ticking, printing, ticking, printing, grabbing lock from standard out, printing, releasing, grabbing, printing, releasing. And then some time passes, then it goes, okay, go ahead and stop. So stop, what does stop do? Oh crap. It goes, hey, I need to print, so I'm going to go ahead and acquire the lock. And this thing acquires a lock. Where is it? That thing acquires a lock. And so these two, let's see if we can even, okay, whatever. This basically, this one acquires a lock, and then print final tick also acquires a lock, and then they have problems. So safe output terminal, and safe output terminal is just derived from self.safe output terminal. For Tokyo reasons, it had to be cloned. because it got moved into a async block which got spawned. Okay, so how to rectify this? That's like the problems lie between here, so you can say problem and here. Where the heck are you? This one. So these two are basically the problem areas. So this one, can I highlight it? Okay, so there you go, this one and that one. These two are essentially your program goes, all right, start the spinner, interval lock, print, unlock, interval lock, print, unlock. All of a sudden it goes stop, lock. If that's also locking, they're going to have issues because they've been, if you think about it, they're both essentially locked by the same arc mutex, which inside of it has stdout, which stdout itself is a lock. So it's like totally way too many locks, but we will unwind this in a minute. But no matter what, there's a problem here. So the solution actually is instead of having stop print this final tick, it must be done by Tokyo select, and that'll essentially smooth out the issues, because this actor, which is a long-running task, will basically then control the output that it generates from the interval, and it'll also control the output it generates from the final task. So that way, or the final tick or whatever it is. So that way, regardless, there won't be any contentions, because this thing, the same chunk of code, is going to acquire the resource that it needs to operate on, and because of the nature of how Tokyo select works, like you're not going to have the interval and the stop run at the same time. So that kind of solves our problem. So that's the solution. And so let's see how to implement it next. Wow, this live coding video has been conversation heavy, but I guess this is a complicated topic. Like some of the other videos I've done are pretty sort of scoped, and but this is a real world example, so real world is messy. Okay, so we have the stop function, or a stop method, and we want to change essentially the stop method so that instead of the stop method doing all the stuff, it should just ask the actor, this task, to do the work. So what we could do is, there's a bunch of stuff that happens related to readline async, which we do not really care about, but this is important. It goes shut down the task if it hasn't already been shut down, and it goes, remember we created this channel, the shutdown channel, so this sends a empty whatever unit to the channel, but actually we don't want a unit, because if you look, the final tick actually, if you look at this, the stop method takes a final message as an argument, and that needs to be given to this actor. So it's going to get slightly, and there's no clean way to pass that final message from the stop method to that actor, because remember that actor got spawned. It's already working. When try start executed, it spawned that actor, and it's just gonna unleashed it. So now when we stop it, what we can do then, if you look at the definition of this, it goes Tokyo broadcast sender unit type, right? So what we can do is you can say, all right, just take an optional string. That's one thing we could do. So here we can just say, oops, actually it auto-completed it correctly. There you go. So it goes, all right, go ahead and send the final message as a string. So own it and then send it to the channel. So that's one half of what we have to do. The second half is that we cannot do this print in the stop method. We have to move it into the this thing. So we just copied and pasted there. Obviously it's going to have some teething issues. So what we can do, note the question mark operator will not work here, because we're in a Tokyo's we are actually in a Tokyo spawn block, so it'll question mark out of this block, which doesn't mean anything. So here, couple things. So here, the shutdown receiver, we are going to get a maybe final message, and then here we can say if let some final message, I don't know what all this is, something like that. Yeah, okay. Let's see if we got the types right. It's a result option string. Okay, no, not really. So we can say if let okay maybe final message equals maybe final message, and then we can say, so then we can say if let something along these lines. So, and then let's get rid of this. Okay, so here's where we're like, so essentially what we're saying is that, all right, go ahead and if there was a final message in there, then we're going to do something with that final message. If there wasn't, we're not going to do something with that final message. So the final message really is just about being able to render the final tick. So here we can say something along the lines of let mute final message is, let's say this is toString, and then if we do get a final message, then we're going to say final message equals final message. So we can say if final message is empty, oops, if it is not empty, this is way too many. This is the same, so I'm just going to use message here. So we're going to say final message equals message, something like that. Just a fancy way of like, we can probably simplify this good, but what we're saying is that, okay, if you set a final message, I'm going to go ahead and use it. If you don't set a final message, then I'm just going to say final messages, none, or an empty string. So here we print the final message, and so actually, you know what? I'm just going to say, let's keep this simple. Say, you kind of need a final message, otherwise it doesn't make any sense. So finished spinner, this area, something like that. All right, and then if we get a final message, then oops, this is not maybe final, this is result. Eek. And then this is final message. All right, cool. So, all right, cool. So essentially, we have final message now, and then we're going to say, all right, render final tick, and this does whatever render final tick does, and this thing is going to say, all right, print final tick, and that does a bunch of stuff, flushes stuff, and so this one will return. Let's say we do like this. And does that, and then okay, so it prints the final tick. And another thing we could do is we could also drop the interval. So like, for example, we can say interval, something along these lines, and let's see, there should be a bunch of errors because I changed the shutdown, the nature of the shutdown. So yeah, this one is saying, all right, expected something with option string, but got unit. So let's see, this one needs to be changed. So it can't be unit. This has to be, what is it, option string. And then basically just do this everywhere. So this one, I think also, what is this? Shutdown sender. Expected struct, unit type, got this. Oh, so spinner active needs to be changed. So this one needs to be option string. Okay, now this one I'm gonna write. That's what I was waiting for. So here we have a bunch of stuff, and it goes, okay, self. So essentially you can't have a self being used here. So the only place self is used here is self.style and self.output terminal. And then, so what we're going to do is we're going to copy these up here. So before the Tokyo spawn, we're going to say let self-style equals self-style clone. And then we're just going to replace wherever we see self-style with self-style clone. And then what's the problem? Okay, self-style clone, perfect. And it's still going to complain because it's saying, all right, you can't do this, mutable, whatever the heck this is, lock, unwrap. This one is okay because this one does safe output terminal lock. So we've already kind of copied the thing, so we can do this. We can say, actually just copy the whole problem line. And we can do this one here. So, and this is just a thing you have to do because we're moving and we're spawning. So a bunch of stuff has to be essentially cloned, or if it's got an arc, the arc has to be cloned before it can be moved into this block. So I think, let's see, there's still more problems because that shutdown sender thing. Yeah, this one is some other stuff and some other code broke because it goes, hey, you told me that I was expecting one of these and you gave me one of those. So we can say this one should be option string. Hopefully at some point these errors will stop. Nope, still going. This one is process line control signal. Let's see what the error is. It goes, I was expecting something with option string and you gave me a unit. Ah, that's why. Option string. That should resolve that issue. Ah, there's more. Let's see. Let's see what this is saying. I was expecting something with a unit type and you gave me something with the correct type. So why were you expecting the wrong type? Let's see. That's why. Because this is old code. So option string. Oh, still going. All right. What is the problem now? This is saying I was expecting the wrong thing and you gave me the right thing. So why am I expecting the wrong thing? Ugh, that's why. Oops. What the heck? Option string. All right, cool. And there's more. Oh, this one is saying somebody was sending a unit, so this should be none. And oh, I think that fixed all the compiler errors. This one is saying that I'm doing nothing with the result that comes back from print final tick, and that's right. Because it's in essentially a spawned block, like there's really nothing I can do, so this is fine. What else is there? I thought there was 2 of these. No, just that's it. Oh, okay, cool. So what we can do is we can just say it like this. I say I don't really care about the result that comes back from this, to get rid of that warning, and then janky. Whatever. Let's just do this. All right, fine, cool. So I think let's close all this up, and that's essentially the gist of it. So if you think about it, the code doesn't really look any different from the calling side, but on the implementation side, we basically made sure that when the stop gets called and a final message, let's say, is sent through the channel, the shutdown channel, then when it picks it up, it will drop the interval, so these ticks will no longer do anything. And that's one way of canceling an interval, is that you just drop it wherever it is. And then this one is we just basically, if this should never happen, like it should really be debug assert that this is going to be some, because we don't have a situation where stop gets called without the final message, so shouldn't have made it an option string, but it's okay. So here, just whatever, we have some unnecessary code. This can be cleaned up later, but essentially the final message is then rendered and then printed. And let's see if this works. So let's run it and see what happens. So this is the, I think, yeah, this is the correct place. So let's just run examples to spinner. Fingers crossed this works. So here we have the thing is spinning, the thing is spinning. Notice it now says, okay, this is a final message. Connect to the server. The thing is spinning, the thing is spinning. And it goes, oh, this is a final message. It works. And we'll run it a couple times just to verify. And this is why I dropped this spinner style dots. I don't really know what I was thinking when I came up with it, and I couldn't figure out a nice use case for it, so I ended up dropping it. So so now I'll run it a few more times, but one thing I wanted to say is that there's a reason why this is wrapped. This is unnecessary amounts of locking, except that this particular code is meant to work with something called readline async, which has this concept of input device and output device resource, and to make that happy, there's an unnecessary lock on top of a thing that already needs a lock. So regardless though, by doing it this way, there is no lock contention for this lock, this one, not that one. This one still, but it's not a problem, because once we've acquired the outer lock, the inner lock is not going to be an issue. So let's run it again and do spinner. And again, the inner lock is for the outer lock and inner lock thing is just because of making it work with something called readline async, but the principle still holds. So notice I ran it again. This time it seems to it's working consistently. So let's see, can I Ctrl+C? Yes, let's run it again. Yep, it's working. So in the real implementation, I got rid of the cursor, because right now, if you notice that there's a blinking cursor, which is unnecessary. So in the cleaned up, refined version, the cursor is gone, so the animation is smoother, and a few other things. But yeah, basically this was the gist of that fix. So there you go, lock contention. Even if it's a synchronous lock and you're in async context, you know, these are things that might be useful at some time on your coding journey. So the next two parts of this video are around Ctrl+C. They're much quicker. They're around Ctrl+C handling. Like, let's say you have a long-running task and you want to interrupt it, and then in the real TUI crate, how Ctrl+C does two levels of interruption. When the spinner is active, you hit Ctrl+C, exhibits one behavior, which is to interrupt the spinner itself, and then that can interrupt the task that was bound to that spinner. If you hit Ctrl+C one more time, it then takes care of interrupting the process. And so this is all handled in a very graceful way with signals. And I'm going to talk about signals and how that comes into play. And that'll be the remainder of the two examples in this video. Okay, so now let's take a look at the Ctrl+C handling in this commit. Actually, I think the code to look at is this thing called upgrade check. And where you can see this in action is, so I have this Rebel Commander crate, which uses the Rebel TUI crate and has an editor, Eddy, and also a program called Git Interactive. So whether you run Git or not, or Eddy, at the end they do a check and look at crates.io to see if a new version is available. And if a new version is available, then it gives the user the option to go ahead and upgrade. So that's what this this code that we're looking at. And when I originally implemented this, let's see, upgrade check, I wanted to provide two features actually. One is that once the upgrade check is done and it's determined that a new upgrade needs to be installed, then let's see, then let's say that the user is presented with the choice to either upgrade, and they say yes, and then that'll kick off the upgrade process in the background. So it'll spawn a Tokyo command that runs cargo install rebel-commander, and then that ends up taking however long. And then while that's doing its thing, if the user presses Ctrl+C, then the thought was, well, that should be aborted. And that's kind of like how this came about. So if you look at the function to do this, I think it's called install upgrade command with spinner and Ctrl+C. So let's see. Yeah, I think this one, let's see, I think this one actually, so it creates a spinner like we just saw, and then it spawns a command, Tokyo command, and I think it's a Tokyo command. And then it does process start. Okay, it starts the process to, okay, that actually looks right. I think this code is the one of the fix already in, but I can just tell you the sort of the main error that was happening, or the problem was that because this piece of code in its older version, this is the fixed version, was using readline async, and readline async was using cross-term event stream, which uses MIO and Linux epoll to essentially get user input from standard in. So the problem was that registers a Ctrl+C handler, and in a process you cannot have more than one Ctrl+C handler installed at any given time. So the bug fix was simply removing readline async from this code block, because there was no real reason to have it here, because readline async, by the way, is the thing that if you say git branch and then you say new, this is readline async. It's a line editor where you can hit up, down, you can edit the contents of the line and so on. And this basically, this whole thing is so like you can say main, and then it'll say, oh, branch main already exists, so I'm not gonna do anything. So anyway, so that's readline async. So there's no opportunity here to ask a user to type anything, so I just removed it. And the fix was to actually, let's see, is this, I think this is Tokyo. Yes, this is actually not the normal command. This is a Tokyo command, and the solution was to use Tokyo command and then say, like, you know, cargo install and the crate name, which is you can just get the crate name from an environment variable. Cargo actually provides this. It's really nice. So essentially it's updating itself using cargo, and that creates this async command, which is not the standard process command. And then once that command is created, what happens is that the spinner gets started. So here the spinner is started. As you can see, try start. Let me just collapse some of this. So the spinner gets started, it starts spinning, command is created, an asynchronous command, and then it doesn't get executed, it just gets created, the command itself, and then it gets spawned. So that's the Tokyo process spawn. And then depending on, let's see what this does. So it executes a command as a child process, returning a handle to it. So usually, and it, let's see if standard in and standard out get inherited, or what I did here. Let's see. Oh, it looks like nothing got inherited. So the current process essentially doesn't show any output from the cargo install command. The standard in is not available, and standard out and standard error are just piped into this data structure. So they're not actually dumped into standard out or standard error. So essentially from the terminal, you won't see anything when this command is executing. So it looks like what spawn does is that executes the command returning a handle to it. So okay, so we get the handle. And oh, I see, it just has a child process. Got it. Okay, so basically this is like if instead of typing cargo, if I had typed something like bargo, then that obviously wouldn't run, and that would result in this branch being executed. That's what this is. So anyway, but if it was okay, if the result contains an okay variant, then inside of it is a child, and then this is a Tokyo. Oh, I'm sorry, this is a standard process child, not a Tokyo. Oh no, it is a Tokyo. Never mind, it's a Tokyo child because this is a Tokyo command. The Tokyo has equivalent to the standard library process struct. So if you use the Tokyo command and you spawn, then you'll get a Tokyo child. So there's a Tokyo. They're just like the regular ones, but with async capabilities. So so here, what happens is there's a select macro which does two things. So there's two things. So it's polling to see if Ctrl+C signal happens, like if the user presses Ctrl+C, or if the child process finishes. So this cargo install might take a long time, like I don't know, 10, 20, 30 seconds, who knows, maybe longer. And so while that's happening, the spinner is going. And during that time, if somebody doesn't do anything, then the spinner will just continue. Once this branch goes, okay, I'm ready with whatever what type is this? I'm ready with the result, the exit status. Then what will happen is that this branch will run, and it just stops the spinner and returns the status result of whatever the status was. And then I think that just prints it out. It doesn't really do anything. This is just a report. Just prints it to the standard out or standard error. But so essentially the happy path is create the command, wait for it to execute. Once it's finished, you just print the success report. But if somebody presses Ctrl+C, then this has to happen. And what this will do is that it stops the spinner, and then asynchronously it asks the child to kill the process, and then checks to see whether that completed or not. So this is another pattern. I've actually adopted this pattern in the spinner and all the readline async stuff as well, where you'll try and start something, it'll do its thing, then you request stop or request shutdown, then you have to wait for it to complete shutdown. So that's a new spinner API. It's much cleaner actually. It allows for clean shutdown. So yeah, this is essentially then how Ctrl+C gets handled. And this is not that interesting, except to say that Ctrl+C handler, you can't have more than one per process registered at any given time. And once you register one, you cannot register it. Like, you can't register another one. You have to like unregister that one. Something along those lines. So basically when this block ends, Tokyo will unregister this Ctrl+C handler. So this Ctrl+C handler won't really do anything like past this, block. So that's how Ctrl+C gets handled. And then another thing I wanted to show is in the sort of the final version of this. Let's go look at this one. Oops, why did I do that? Wow, undo close tab worked. This is a great terminal emulator. It's called Blackbox. It's great. I have another one called PTYXIS. That's really good too. I'm going to do a terminal emulator review one of these days. I have so many. Okay. So this one, core spinner. So I think this is the wrong folder. Let me go to the latest workspace. Worktree, sorry. I'm totally gonna make a gitty workspace command soon. Okay, so let's go look at the main one. So we say code insiders, tab. So if we look at this, let me zoom in. Uh-oh. That's not good. vscode locked up. That doesn't usually happen. Okay, let's reuse it then. Okay, so this is, let's see, which function am I looking for? This is the example which shows how channels. Readline async example. Got it. So I think this is the one. Yeah. Okay, so which line number? 138. Aha, I see. So I think this is the, yeah. So this, I think, okay, let me show you what this does. So this is the, let me go to the correct folder. Spinner, downloads. Okay, what we want is to go to the main branch, basically. So, okay. So here we can go to the TUI folder and then run examples. And then we can pick this one, I think is readline async. Yeah, that's the one. Okay, so here, if I say spinner, I can press Ctrl+C and it terminates the spinner. But while the spinner started, it actually pauses output. So this is asynchronous standard out. It's something called a shared writer. This is now we're into the readline async territory. So with readline async, once you start readline and you call readline, because it's async, it doesn't block. And so while other tasks could be running that need to emit output to the standard out and standard error that's managed by that readline. Obviously, the standard in is also managed by that readline. You can pause the standard out and standard error, and that's what the spinner does. So when spinner is running, it actually starts emitting output in the background, which you don't see while the spinner is running. And then what it does is once the spinner is finished, it just flushes out whatever content has been queued to the async standard out, which is pretty cool. But what you could do is you could just hit Ctrl+C and that'll interrupt the spinner. And then if you hit Ctrl+C again, that just exits the task, or sorry, the program, the readline async. And this is that example code actually. So it makes that prompt. Then it starts a readline async, something called the readline async context. With a readline async context, you can get shared writers from it that you can use to essentially defer output to standard out and standard error that have been paused. If they're not paused, then it just works like the regular standard out and standard error. And using this context, so maybe we should just call it readline context. Using this context, you can also simply, I think this is like maybe, and this is the readline context. Oops, there we go. So using the readline context, you can do all kinds of things. You can manipulate the history that line editor will have. So you can, like, for example, if you run readline async, if you press up and down, I pre-populated these with commands basically. So if you look, this one says start printout, stop printouts, stop task, start task. So essentially, these are all like pre-populated in the line editor's history, and that's all part of this readline async context. So the thinking is you start one of these contexts, you populate it with your history, or you do whatever. You can make your own shell using this, and then when you're done with the REPL, the read execute print loop, then you drop the async context, and you can continue with your code. or do whatever else, and it'll take care of managing the raw mode in the terminal and all it cleanup it needs to do. It's non-invasive. So so here we populate the context with commands, so that when you press up, you know, like for example, you can see there's like a tree command, and when you run that, stuff happens. So that happens here, and then I mean here, and then once all of that is set up, there's this readline. You can call it readline. This is the main sort of where this is the main thing that happens. And what it does is that it essentially checks to see if Ctrl+C was pressed, and if it is, then it shuts itself down, which is fine. But for the spinner, when the spinner is running, so like for example, if you look at where's the spinner? There it is. So if I type spinner, what it does is it'll runs this function, and what this does is that let's see, spawn task that. So I think this one, oh yeah, okay. So this one creates a async block and spawns it and tells it to display the spinner. And then a very similar kind of thing. What it starts at interval, and then every tick at the interval it displays something. So now here actually, when Ctrl+C is pressed, the behavior is a little bit different. And the reason for that is that if you look at readline itself, the readline, let's see. So when you say try new, this thing, it sets up a whole bunch of stuff. And one of the things it sets up is this coordination between itself and spinners. So if you start a spinner and you tell the spinner that you're running in a readline async context, the first time you press Ctrl+C, readline will actually tell the spinner to stop spinning, rather than Roomba started. So it'll tell the spinner to stop spinning, and then once the spinner, you can then, once the spinner stops spinning, like you can have it essentially resume the pause to standard out and standard error, the async standard out and standard error, and then they'll essentially go back to, it'll flush whatever was queued in there if anything was flushed, and then the program will proceed. And then if you press Ctrl+C again, readline will intercept it again and then do something else. So this is all happening in readline. So so this readline context, it's kind of complicated. The context actually, let's see, this is try, where is it? Let's look at, okay. So this is what's happening. So the readline, this is the one that actually has try new. So as a user of this API, you instantiate one of these, and that'll actually give you a tuple with a readline in it, which is this thing. And if you look through, it's essentially it's an actor, and it spawns a task. So when you say when you create a new readline instance, it does a whole bunch of stuff, and one of the things it does is that it spawns a task to monitor and control its state from other actors. And so so here when actually, let's see, so if you actually look at the readline function, where is it? I think, where is readline itself? There it is. Okay, so it actually runs this function, and there's a bunch of stuff it does, and you can see here is the Ctrl+C handling. So basically, when it gets its events from MIO via crossterm. Crossterm is MIO. And so gets Ctrl+C, for example. It checks to see whether it has a spinner associated with it. And if it does, then it tells the spinner to shut down. And if not, it just continues. But so yeah, that's how that magic works. And if there is no spinner, then it shuts down. It basically notifies whoever is calling readline saying, hey, the user is interrupted. They press Ctrl+C or Ctrl+T, do something about it. So essentially that's how that works. So it's a bit convoluted. I'll do more videos if there's interest. Please let me know. Actually, this is a good time to talk about the Discord as well. So that was actually the end of the video. It was not very heavy with coding near the end. I just wanted to talk about some of these patterns I've seen. So if you have questions about this video or other videos you want to see, I actually created a poll on YouTube and a few people responded, so I might actually continue doing that to gauge interest on what folks want to see. But a more direct way is just if you just go to Discord and then ask your questions. There's a bunch of different channels. I also post information in Discord that I can't fit in the video descriptions and other information. So I try not to use it too much, but it's mostly for like information and feedback, information that I want to share and feedback that I want to get from you. So if you have any requests on other videos you want to see, especially related to the Rebel TUI crates or just any other topics in general, please share that there. And then if you like this video, or please give it a thumbs up. And if you like the style of this video, please subscribe to the Developer Live channel, and then you'll be notified when I drop more content. And other than that, I have the comments disabled on YouTube, so the only way to really provide feedback is directly via email, GitHub issues, or Discord. And then I also have another, where is this? I think this is, let me see if I can find it. It's in Rust Scratch. I think it's here. I have a bunch of issues which outline all the YouTube videos that are in the pipeline. So if you have anything you want to add to that, or any other videos you want to see, feel free to add a comment to the to these issues, or you can share your thoughts and comments with me on Discord. So yeah, that's all I have for today's video. Thanks for watching, and I'll catch you in the next one. Have a good day.